Hi everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 3 of this time response analysis, right? So in the previous lecture we analyzed the first order systems. Okay, now we'll do the analysis for second order systems. So before that I missed a one point that about the first order system, right? It was about the settling time. Even though we will study about settling time for the second order system also, but for the first order system also I will give you a brief idea about settling time, right? So what does settling time mean? It means the time at which the actual output reaches within 2% of the desired value. I mean 2% error band. So this 2% is basically the error band, right? Okay, so this 2% is the error band. So what does this mean? For example, let's say my desired output is 1, right? 1, and it reaches to 0.98 after let's say 2 seconds. So that will be my settling time. Okay, that will be my settling time. Now like this settling time takes into account all of the things, right? Like time delay and other non-idealities. So settling time for this case, right, in this case we have to take care of TD also. One thing we know, like I think in transient Himanshu has taught you that at 4 tau time my output like reaches steady state almost. We can assume it has reached steady state. That is basically the 4 tau time, right? Like here the 2% error band is, if you find the time, like if you put here 4 tau and if you check, it will be 0.98 times B. So it is around 2% of the steady state value B, right? So basically for a first order system with a unit step input, okay, my settling time will be 4 tau. Okay, it will change depending on the order. Okay, second order system it will change, definition will change, right? So for a first order system the settling time, okay, without delay only the due to the first basically general form, right? First general form, okay, without delay, without any like gain you can give, right? DC gain you can give, but without delay my settling time will be 4 tau. Okay, valid for unit step response like for first order system type 1. Okay, so yeah, this is basically my settling time, right? So now we will go to the like main topic of this lecture, basically the analysis of second order system. So for second order system, right, first we will understand why are we discussing about second order and first order system. So first of all, right, the analysis of second order system, like as you have already assumed, will be difficult than the first order system. Now the analysis of third order system will be even more difficult than the second order system. So what we do is that we use the principle of like concept of dominant pole that we studied, right, in the chapter 1. I hope you are revising. So we use the concept of dominant pole, and with the help of that we convert my third order system to second order and then do the analysis, because obviously like doing the analysis with third order system will be really difficult. Okay, so we do some approximation, that is the dominant pole approximation, right? So yeah, why we do to measure the performance of the system, right? Just to from third order system measuring the performance, like calculating the performance of the system will be difficult. That's why to calculate the performance of the system we convert it into second order system, right? Now first thing is that this is a practical knowledge. Basically if you are checking for the performance of the system, right, the first condition is it should be stable. If it is not stable, as I told earlier lectures also, if it is not stable, then how can you measure the performance of the system, right? How can you measure the performance of the system? So first condition is the system should be stable, then we will go to the next step, that is measuring the performance, basically the time domain performance. All those we'll discuss in the next lectures. In this lecture I will basically give you a brief idea about second order systems, right? And about damping also, because damping is a really important concept in this chapter. Okay, so first is I will compare between the electrical components and the mechanical components. So electrical components we already know, we have 3 components, right? And other components also we have, okay, and other parameters also we have, but 3 components we know, R, L and C, right? So what does a resistor do? Tell me, what does a resistor do? It resists the flow of current, right? It resists the flow of current, okay? It opposes the flow of current. And what is dashboard? Like, if you have heard the name, that is good. If you haven't, then basically, right, dashboard is basically like a, does the same thing. It resists the change in position, okay? It resists the change in position, okay? Velocity, basically it resists the change in velocity. So this is what dashboard is. If I try to move it with a velocity, then it will give a opposing force to me, so that it will not move. So this dashboard is used where? It is used in you see car window, those blades, right? There these are used, right? Okay, so this dashboard is like related to this resistor, okay. Why? I will explain. Okay, we don't need to go into too much of detail to this, because this is not that important for gate perspective, but to get a like good idea of like what we are doing and why we are doing, right? That's why. Now this inductor is basically, it opposes the rate of change of current, right? It opposes the rate of change of current. Now what does this relate to in mechanical components? It relates to mass, okay. So I will write the formulas for each of them, then we'll understand. So like what is resistor? Resistor is equal to VR equals to I times R, right? So this is the equation for resistance. So it is relating the motion of charge, right? Motion of charge and the electromotive force. So this voltage in mechanical system is equivalent to force. So what is the equation for this dashboard? What is the equation? Dashboard, right? So dashboard is equals to force FD equals to mu times V, okay. Now what does this V mean? V is the like speed, right? Change in position, dx dt basically, okay. Change in position with respect to time. Now what is this current? Current is flow of charge with respect to time. So for mechanical and electrical components, the V and I are relatable, okay. So this is like, okay, I can write like this, current, and basically I will say this, I will not write here, okay, I will still write. So current and velocity are relatable, right? Current and velocity are relatable. Now this VR, right? This VR. So VR is force. So here it is related to the force. Basically VR is related to force. So voltage is related to force. Okay. So yeah, that is why this mu is basically dashboard, okay, coefficient basically, and this is R, okay. This R and mu are relatable, okay, because this is also relating force and velocity, and this is also relating like electromotive force and basically change in flow of charge, right? So yeah, then this R will be equivalent to mu, that's why. Now for inductor, right? So you are surprised how is it related to mass, okay. So like okay, let us do a quick proof, because this is just like not that important. So in what is the equation of inductor? It is L dit dt, right? L dit dt, okay. Now one thing we know since our childhood, the force equation, force equals to mass into acceleration. If there is some mass and applies a force, it will have some acceleration, right? So yeah, force equal to mass into acceleration. Now what is this A? A is the rate of change of velocity, right? So it becomes m dv dt f. So this is f, and this is also force, and this is change in velocity, and this is also change in current, change in flow and change in velocity, both of them are equivalent, okay. So my mass will be equivalent to inductor, okay. Okay, inductor mass will be equivalent to inductor. So yeah, that is it. Now for capacitor, right? For capacitor, what is it relation? Capacitor's relation is simply C dvc dt equals to IC, right? And what is the spring relation? Basically, what is the spring relation? Spring, right? Spring is related like this one. I hope like you have studied I think in semester also, first second semester, there is also some mechanical problems, or like in 11 12 there is anyways mechanical problems. So spring, right? spring force, how is it given? So F spring equals to K times X, right? Now what is this X? X is the change in position, okay? X is the change in position, and this K is the spring constant. Now if I differentiate both of this LHS and RHS, right, what do I get? I get dFs by dt with respect to time equals to K dx by dt, right? So what does this become? This becomes my velocity v, right? And what is v? V is equals to IC only. So, and this is c dvc dt. So this will like, okay, so how will it relate? So I will write here like 1 by k will be equals to c, right? So my 1 by k dfs by dt will be equals to dx by dt, right? So my 1 by k will be equals to c basically. So now, right, now I found the equivalent between capacitor and this spring constant. So basically I gave you a flavor of what are the equivalent in like electrical systems, right? So like I gave you an idea what is dashpot, what is mass and spring in relation to the electrical systems, okay? Why? Because I will derive an equation with the help of these three components, and that's why I have had to go through this a bit, right? So basic analogies you got, right? So what is voltage? Voltage is like a force only, right? Force only, and current is the flow of charge. So that's why the flow is given by velocity and voltage is given by force, okay? These are just correlations between mechanical system and electrical system. Now, right, now we'll see like what is the main motto of this chapter. Basically main motto of the chapter is to understand all these waveforms, right? All these waveforms. So I think you have already seen this in your semesters or something, but to understand in a better manner. So what is this? Basically this is the response. What response is this? This is the unit step response of a second order system for varying the damping factor basically. So what we see is that there is some like there is some oscillations, right? There is some oscillations. So what do I mean by oscillations? Oscillations mean that, let's say like this is my steady state, right? So around the steady state all of them signals are oscillating. These are basically different signals with different damping factor for the same system, right? I'm applying different signals for the same system with different damping factor. What is damping factor? Obviously end of this chapter we'll understand, but I'm just giving you a brief overview, right? So around this one, right, I am always oscillating, okay? Like this is some response. What is this response? This is under damp. So as I can see, there is quite a bit of oscillations if I have a under damped system, okay? Now what I see is that this system, right, this is reaching my steady state but very slow, right? It is taking too much time. There is no oscillation here. It is not revolving around the steady state point, but it is reaching my steady state point very slow. So what is this purple line? This is the overdamp. So my damping has been overdone, right? And then, right, I have like this one, which is always oscillating around. It is never ever reaching the steady state basically. So this is the violet line. So violet line is undamped. So there is no damping itself. So what does actually damping mean? So damping, right, damping actually means that in real life systems there are always some force, right? Not force, sorry, friction, right? Friction. So that is basically what damping means. What happens is, let's say like I will give you one like a mechanical example and then one electrical example, right? So what is a mechanical example? Mechanical example is basically you like have a ball in hand, right? Ball in hand, and you like put it down, okay? Then what happened? It again bounced back up, then again down, then again up, then again down, and slowly what happened? It reached steady state. Basically it stopped, right? Okay, in the ground. But what was happening before that? It was going up down, but that was also reducing, right? The height was reducing after each step. The amount of by which it goes up, and the amount by which it goes down, okay, it keeps on going down, right? Why does this happen? If this I would have done in a place where there was no friction, then if I dropped a ball, right, it will again go up to the same amount and again keep on doing that, right? Keep on doing that, okay? So but due to friction, what is happening? Energy is being lost, and that's why that is the concept of damping, right? So bit of energy is being lost, and finally it is settled into a steady state. And like from this example also we can understand, if I apply some force to this mass, okay, apply some force to this mass, what will happen? Apply some force, then leave this, right? I applied some force and then I just leave the mass, then what will happen? Some force will keep push this mass here, then what will happen? Again this will come back, right, due to this spring and this dashpot. This dashpot will also oppose the basically direction of this mass basically at this end, and spring also, as there is some displacement, this one also will oppose, right, due to displacement. This will give it a force in this direction, left hand side, and this dashpot, as there is some velocity change, right, there is some velocity change, so this dashpot will also come into action. This one will also give it some force in the opposite direction. So what will happen basically, right, I will give a force here, now this mass will come here, then again it will come back to here, okay, then again it will come back to here, then again come back to here. Now at certain point it will again reach its steady state, okay. So but what is happening before that? Some oscillations are happening. Now the main thing is to reduce those oscillations, right? To reduce those oscillations we use the concept of damping, okay. This dashpot helps us reduce the oscillations. Now as we can see, there were too many oscillations, right? So if I want to reduce this oscillation, I use a more damped system so that I can reduce my oscillations. But if I use a like highly damped system, then what will happen? My system will reach steady state much slower, right? So there are trade-offs there, we'll understand while studying this chapter. So yeah, that was basically the motivation for this chapter, right? Now like I will also give you an example of, let's say like AC, right? The same example. So you turn on the remote and you want like it to get 24 degrees centigrade, but what is happening is that basically your room temperature is 30. Again the same example, so we have 6 degree of error, so it cooled it down so much, okay, cooled it down so much that it reduced to 18 degrees, okay. Then like again I have to again stop the AC, so like the automatic, the AC, like the cold air that was coming, it stopped coming, right? So again what will happen is that again my temperature will increase, then again it will go to, let's say 26, and again it will keep on oscillating, okay. Now if I increase the damping, then the difference between the actual point and the difference between the actual output and the desired point won't be too much oscillating, right? Oscillations will reduce, okay. So yeah, that is the main purpose of damping. The main purpose of damping is to reduce oscillations. And the main thing is that this undamped, right, this sinusoidal behavior, we will actually not achieve this. Why? In real systems we will actually not achieve this. First case is obviously we'll do derive, then there also we'll understand like why. Because for this to occur, right, the basically friction has to be 0. Now what provides friction in mechanical system? In mechanical system obviously like friction provides friction, okay, like in land everything is friction, right? Air has also friction, air drag, everything. So energy is being lost everywhere, right? Everywhere, so that's why like in real system I can't, mechanical systems I won't be able to make my friction 0, okay, it is impossible. And what about electrical systems? In electrical systems friction is less, but what is the problem? My resistance, I can't make it completely 0, right? Completely 0 I can't. Inductor has some also resistance with it, capacitor has also some resistance with it, right? So making it 0 is not possible. That's why what you see is we make some oscillators, right? We make some oscillators, but those are not perfect oscillators. So what we have to do is we have to place a amplifier with it so that it can compensate for the loss, right? So I have an oscillator, right? Let's say LC oscillator, but obviously that is not ideal, there is some resistance with it. So what I do, I place an amplifier with it to compensate for the lost energy in the practical resistor, right? So that's how I make the oscillator. So yeah, that was the basic concept of damping and all those things. So damping will always be present no matter what, okay. Damping will always be present because I can't make R equals to 0 in an actual circuit. Obviously in this theoretical part I can make, but in an actual circuit R, some part of R will always be there, hence there will be some damping, okay, due to that R, because it opposes the change in current, okay, and not change in current, sorry, it opposes the flow of current, okay. So yeah, that was the basic thing. Now let's analyze this mechanical system, okay. Like let's say I give this one a force of F, right? I give this one a force of F. Okay, so now I will analyze this using like some F force is actually acting in this. So I will analyze this using free body diagram. So I think that you have studied in your first sem or second sem, I don't remember. Okay, so if I analyze this using free body diagram, right? Analysis using free body diagram, what do I see? So like first I will make the body. Obviously this is my mass M. Okay, now this I have applied some force. Okay, I have applied some force F of t. Okay, function of time. This force is basically function of time. Now due to this force, right, my mass has some inertia, and due to this inertia force, what will happen? A force in opposite direction will come, because this mass doesn't want to change. Just like you don't want to go out of bed, right? You want to like sleep in bed itself. So this mass also doesn't want to change its state, right? So it will give a opposite force of Fm due to inertia, which will be equals to basically mass times acceleration, right? So yeah, this is Fm. Now what are other forces? I have this spring, right? I have this spring. So spring will provide some spring force, right, which will be equals to kx, as I discussed the formula earlier. So spring will provide some Fs of t, which will be equals to kx. Now what will be my other force? My dashpot force. So this will provide some force, as there is some velocity, right? There is some velocity in the mass. As I am giving it a force, there is some constant not constant velocity is changing, but there is a certain velocity, right? Due to that velocity, this dashpot will try to pull it back again. So I have Fd over here. Okay, which is equals to time. Okay, so yeah, now what do? I do apply the equilibrium, right? Basically force on the LHS and the RHS, all of them should be equal to each other, right? So then only I'll get the equilibrium condition. Okay, so my left hand side has Fs of t plus Fm of t plus Fd of t. Okay, and right hand side has Ft. Okay, the force that I'm applying. So what is this? This is basically the input, right? And what are these? These are basically the responses that I'm getting, right? Due to this input, I'm getting some responses. So these are my 3 responses. So what I will do now is that, like, what response I want to see, right? Exactly, input is one only, but what response I want to see. So I will choose here the spring force. Basically I want to see the spring force. So what I will do, I will make all these forces, right, in terms of Fs, so that I can write a differential equation in terms of Fs only. Okay, so like what is Fs equals to? Fs spring force equals to k into x, right? And what is this Fd equals to? Fd equals to mu into v, which is basically equals to, like, if I do the this is simply Fd equals to mu dx dt, right? So this is basically the differentiation of this displacement. So if I differentiate this term, right, then I will get differentiation of x with respect to time. So this is dfs dt equals to k dx dt, right? So my dx dt is basically equals to dfs by k, right? So like okay, I will replace this dx dt up here. Okay, so I will write Fd in terms of Fs. So Fd equals to mu by k dfs into dt. Okay, so this is basically my Fd. Okay, so yeah, this is my damping force. And what is my Fm, right? Fm, force due to inertia. So let me write in different pen. So my Fm, right, Fm is equals to mass into acceleration, which is dv upon dt itself. Okay, and basically, which is basically I will differentiate this again to get it in terms of position, right? So which is equals to if I differentiate, okay, like this is equals to fm equals to m into d square x of dt, right? D square x of t of dt. Okay, so now, right, I will differentiate this equation again. Okay, so what do I get if I differentiate both sides this equation again? So I get d square fs by dt square equals to k d square x of t dt square, right? So this is what I get. So now, right now, basically I'm getting d square x dt square in terms of like fs. So I will replace this d here from this equation, right? So this will be simply okay, let me put this bit above, use some other color. So this will be fm equals to m by k d square fs by dt. Now this is not that important, just to show you one example, right? Damping example. This is one practical real life damping example, right? So due to this dashboard, it is providing some damping, right, to this mass, right? Because this is resisting the velocity, okay, this is resisting the current, so this is resisting the velocity. Okay, that's why this dashboard is providing some damping to the system. So just to show you the practical approach, that is what I am doing. In electrical circuit also I will solve one question like this, so there will understand it. So this is my fm. So what I will do, I will replace in equation 1 the value of fm and ft. Okay, so fm was this one. Okay, I don't have space. fm was this one, and what is fd? fd was this one, right? This one. And fs is fs itself. So this is fs itself, which is equals to what? My input, right? So this is my, basically that's how we write a equation, right? That's how I write a this second order equation, differential equation. Okay, from there. So like if you're not understanding, this is just force equilibrium, and if you're not understanding, then don't worry, skip it, just to give you like a basic idea about damping and all those things, and why we have to study this, right? This is studied in mechanical engineering also. Okay, so this is important for them also, and for us it's important in our circuits. Okay, I will solve the circuit and then obviously in the next slide. So this is fn, this is my input. This is not fn, actually this is only f of t. So f of t, this is my input, and like and this is my response. Okay, this is the response that I am measuring. So yeah, basically, right, what I will do is, like, this is my differential equation basically. Okay, this is my differential equation. So yeah, I will not do anything. Like if you want to find transfer function, you can do like a Laplace inverse of this and then find the transfer function. So this is how we solve for differential equation. But now I will solve the real thing. Okay, the series RLC circuit. So like in series RLC, I haven't solved it there, like in network theory, I think. So here I will solve the totally with the help of differential equation. Then I will apply Laplace transform, right? So first, like, what is the filter type? So this is, right. So if you can guess, like, how do we define filter? Okay, like first thing what you do, you find the gain at s equals to 0 or the gain at s equals to infinity. If you don't understand anything, then don't worry, skip this. Okay, if the people who are understanding, then this is for them. So if you find the gain at s equals to 0 and s equals to infinity. Now if at s equals to 0 you have a gain and s equals to infinity you don't have a gain, then this is a low pass filter. The gain is 0 at s equals to infinity, then it is a low pass filter. If at s equals to 0 your gain is 0 and at s equals to infinity you have some finite gain, then this is a high pass filter. Now if at s equals to 0 you don't have gain and at s equals to infinity also you don't have gain, then what does that mean? So my graph will be something like this, right? Somewhere in the middle it will have some gain and then again it will decay down. So this is a band pass filter, or if the band is very nano band, it is known as notch filter. Now if there is some gain at 0 frequency and there is some gain at high frequency, it is going like this then. Okay, sorry, it was not the notch filter. Notch filter was this one. Sorry, notch filter was this one. Okay, that was that is known as narrow band filter. Okay, so this is known as the like a band stop filter. Sorry, this is known as the this is known as the band stop filter, and this is known as the band pass filter, right? Band pass filter. So for a particular band, it is not passing the band, right? And this is passing the particular band, right? That's why. So if you don't understand any of this, this will taught you in analog electronics, right? Like just to give you a like basic overview of that. That's why I explain it to you. If you don't understand, don't worry. This is not important for this one. So like we call this a, just to tell you that we call this a second order low pass filter, just to make you understand. That's why I had to explain all those things. So this is called a second order low pass filter, right? This is called a second order low pass filter. Now what I'll do, I'll simply apply KVL here, KVL. So my VC is the output, okay, that I'm response that I'm interested in, and my VI is the input. So VR of t, I will simply apply KVL. VR of t plus VL of t plus VC of t should be equals to my input, basically VI of t, right? So now, right, I will, like, the current is same everywhere. I can write in terms of current, right? But VC I can write. Okay, why, let me explain. So like some integration term will come. So basically, right, VR will be equals to I times R, okay, I of t times R, and VL is L di dt, okay, plus VC is only VCT. Why I can change, like VCT will be 1 by C into integration of I of t. I don't want to bring here integration terms. I only want to work with differentiation terms. That's why. So like VCT anyways I don't to replace, because other terms I of t I will write in terms of VC of t, right? Because I am measuring the response of capacitor voltage. That's why. So this is VC of t is equals to V of t. So now, right, what I will do, what is basically like VC of t equals to, so VC of t, like not VC of t, so what is the relation for capacitor voltage and current? It is, I wrote it earlier also, C dVc by dt equals to IC of IT. Basically IC is same, only I. Okay, this is a relation. I will replace I with this one in all of them, right? All of them. Okay, I will replace in all of them. So if I replace I here, this will just simply be replaced with C dVc by dt. So this is C dVc dt, okay, and what is this, like we have also another R, so this is R also. Now we will add, so here I have differentiation of current. So what will differentiation of current? It will be double differentiation of voltage. Basically if I differentiate this equation again, what do I get? So di of t of dt will be equals to C d square by dt square, basically. Okay, so this is what I get. So yeah, I will replace this like here. So this is C d square VC of t by dt square, basically. So it is dt square. Then what I can replace here it with is like this is L also. So L will also come here, right? L here is remaining. So now third term is only VC of t, nothing changes here. Okay, so and this is not 0, this is input, right? So now what I will do, so basically, right, what I will do is I will firstly make the coefficient of the second order differential 1. Okay, so why? Because I will take the Laplace of this after this. So coefficient of the highest order power is generally 1, right? That's the standard format. So we will divide by L square C, sorry, not LC on both sides. So what I will get, VCT dt plus if I divide by LC here, so what do I get? This is R by L dVc t dt plus simply again I will divide sub VL of t by LC equals to Vi of t also is getting divided by LC. Okay, so yeah, this is basically if I divide it by LC on both sides. Now what I will do, I will take the Laplace transform of this one. So like if you know the formula, that's well and good. If you don't know, just remember this one. This will be taught to you in signals, right? Just mug up this one for now. This will taught you in signals, like the Laplace transform of double differentiation of a signal. What is the Laplace transform of double differentiation of a signal? So basically, right, it is s square, okay, into Vc of s, but we have other terms also, the initial conditions. So this becomes s into Vc of 0, okay, in the time domain. So this is in the time domain, right? This is not the Laplace domain, minus Vc dash of 0, okay. What does this mean? This means the differentiation of the time domain expression for capacitor voltage, then putting t equals to 0 on that equation, right? So this is this one. Now plus this was only for this one, right? Only for this one. That's why this is a bit lengthy. Now like for finding the transfer function anyways, I will make the initial condition 0. So I could have skipped writing this, but still I will write this, right, to make to teach you that the Laplace transform of this one, right, is in the form something like this, not just simply this one, not just simply this term. Other terms also come, but we ignore them because we are interested in the transfer function, right? Now if we are interested in the transfer function, then I can ignore my initial conditions, right? Initial conditions are made 0 for finding the transfer function of the system. So yeah, that was the basic concept. So this is R by L here, and again there is some S Vc of S, okay, S Vc of S minus Vc of 0, which is in the time domain expression, right? Minus Vc of 0. So yeah, so this is basically this. Now I have third term, right, this one. So this one will be directly Vc of t, like Vc of S only, because this is Vc of t. So this one will get converted Vc of S by LC, right? So which is equals to R by L. Oh sorry, there is also like 1 by LC into Vi of S, right? 1 by LC into Vi of S. Okay, so this is also this one. So now, right, now what I will do, make all this 0, okay, because I'm interested in finding the transfer function. So for transfer make initial conditions to be 0. Okay, but to make initial conditions to be 0, right? So yeah, if I make those 0, what am I left with? I am left with Vc of S plus R by L S Vc of S plus Vc of S by LC, right, which is equals to V of S by LC. Now I will just take it common and find the ratio. The transfer function T of S equals to Vc of S by Vi of S, which is equals to 1 over LC divided by S square plus R over L plus 1 by L. Now sorry, there is also S here. Now can we see that there is a low pass filter here? Can we see from the frequency domain expression? So what does low pass filter mean? It means that I only pass the low frequency signals and I don't pass the high frequency signals. So for lower values of S, let's put S equals to 0. If I put S equals to 0, I'm getting gain of 1. Now if I put S equals to infinity, this is the higher order. Okay, in the numerator I don't have any power of s, so this will go to 0, right? So I get 0 again at s equals to infinity. So yeah, this satisfies the low pass filter. Okay, so this was a transfer function for a series RLC circuit. Okay, when I'm taking the output from the capacitor voltage. Why did I give it to you? Because like now I will write the general governing equation of a second order system, and the form is in this form only, just the names have been changed. Okay, this, right, we will understand this later. This is known as the natural frequency. Okay, natural frequency of the system, and like this term is equals to 2 zeta times omega n, and zeta is known as the damping factor. So these two terms are very, very important for a second order system. Okay, these two parameters, so these we will understand. Okay, by writing the governing equation, and then we'll understand why is this called damping factor and why is this called the natural frequency. Okay, what do you mean by natural frequency? So yeah, basically this is my response, and this is my input, right? So now I will write the governing equation for a second order system. Okay, so like this governing equation is generally written for vibration structures, basically where friction is present, right? Okay, these are generally written for vibration structures. So what is the governing equation? It is d square y dt square plus 2 zeta omega n dy omega n, which is equals to simply the input, which is also multiplied by omega n square into u of t, right? So why is this form? You can see that this is also multiplied, right? This is known as the natural frequency. So here natural frequency is getting multiplied, here also natural frequency is getting multiplied. That's why I write the form like this one. Okay, omega n square, and this 2 zeta omega n is this one. We'll understand this, what is zeta, what is omega n, that we will understand, just to show you the similarities between, like, not this one, between this one and this one, right? We'll take the Laplace transform and we'll do the same thing again. Okay, so here what is zeta? This is known as a zeta. Okay, this is the damping factor. My, like, I can't write zeta that much like greatly, right? Damping factor. Okay, this is my damping factor. Now what is omega n? Omega n is basically known as the natural frequency. Okay, so this is my omega n basically. So what is my transfer function, right? So again, right, if you do the in Laplace of this one, you will get to see that transfer function is like this one only. Above I have one natural frequency, so like this one, right? This is not the natural frequency, actually the under root of this one is natural frequency. Sorry, my mistake. The under root of this term is natural frequency. Okay, so yeah, that was my mistake. So here it will be square of omega n square. Sorry, I mean square of omega n, right? Because this was the what I am saying. So the under root of this one will be natural frequency. So under root of this one equals to omega n, but I have not under root, right? I have a square term, so this will be omega n square. That's why. So yeah, this is omega n square. Now what else I have? I have s square here. Okay, plus this will be 2 zeta omega n plus again omega n square. Now if you check here also the d secant is 1. Okay, you put s equals to 0, you get d secant 1, and high frequency is 0. So this bottom time, right, we already know it, right? If we equate these two equals to 0, then we will find pole, right? So let me copy this. We'll find the location of poles. If we equate this to 0, we'll find the location of poles, and this equation is obviously known as the characteristic equation. This is very, very important equation, so keep this in mind. Okay, keep this in mind. Equation. Okay, so yeah, this was basically it for the general equation of a second order system. Now this is the block diagram structure. Okay, this is block diagram structure. from here, if you find the transfer function, right, you'll get the same transfer function. Let us find the transfer function from this point, right? So this is the open loop gain, okay, of this block, and we have a negative unity feedback. So I will get the same transfer function, okay. So my T of S will simply be equals to by S square plus 2 zeta omega n s divided by one plus omega n square by S square plus 2 zeta omega n s, which is equals to omega n square S square plus 2 zeta omega n s plus omega n square. So this is what I'm getting, right? So yeah, this is basically my transformation. So here, right, here, so here my DC gain is 0. DC gain, not 0, sorry, DC gain is 1, right? DC gain is 1. Okay, why? You put S equals to 0 and you see omega n square are cancelling out, right? So this is the standard equation. Now what if I have a non again I said 0, sorry, DC gain is 1, okay, DC gain is 1. So what if I have DC gain anything else than 1, okay? So if DC gain equals to k, right, what if my DC gain is k and which is not equals to 1, okay? So now I will replace my transfer function like this one, okay? So this was the standard form, okay, standard form. Now this, right, this transfer function will be basically k into omega n square divided by S square plus 2 zeta omega n s plus omega n square, okay? So this is basically my transfer function. So this time, right, here, like in this case, in case of standard form, my transfer function is a function of only omega n and zeta, okay? It does not depend on anything else. But here, right, my transfer function becomes a function of, let me write this in different color. My transfer function is a function of k, which is the DC gain, omega n and zeta, okay? This is known as the DC gain, okay? Okay, so this may happen, right? DC gain isn't 1 for the system, so you have to convert it into a non-standard format. So this is a non-standard format for a second order system, right? Non-standard format. So you have to convert this, okay? We'll do few questions from there also, you will understand, right? So yeah, this was for this one. Now let's say I have a time delay in the system, right? There will be some delay, right? Always there will be some delay from giving the input, then I'm taking the feedback, and it is going through all the system. There will obviously be some delay. It is not possible without delay. So if I have some delay, so now T of S has delay of TD, right? If T of S is delay of TD, so my T of S will be equals to k omega n square divided by the same equation again, 2 zeta omega ns plus omega n square. Now you tell me what will be different here. If I just simply add a delay, so what will be different? We will just give a exponential signal, right? We'll just multiply some exponential signal that will just simply provide a delay in the time domain. So multiplication in the frequency domain with exponential provides us delay in the time domain, right? So that is what I am doing. So this time, right, my transfer function will be a function of a lot of things. My transfer function will be a function of k, zeta, omega n, and this time delay also. Okay, so it will be a function of like 4 things. So this is also a non-standard format, obviously, but these are practical systems. Okay, there is delay in system and there is some DC gain. Okay, DC gain isn't always 1. So yeah, this is also a non-standard format. So you might see like we are not doing much questions in the first few lectures because mainly, right, this time response is a bit theoretical. So I will try to like give you more lectures to like finish this up quickly. You just sit down with a rough note and there you like write things that you don't understand, or like things that are key point that I missed to write and you want to like write in your notes, right? That's what you do. So like one more thing, I write it here that yeah, this dashboard is related to register, that is the change in flow. So that I already explained, right? So like this dashboard basically provides a damping in mechanical system and this register provides the damping in our electrical system, right? So yeah, that was I wanted to convey because it resists the flow of current, but we want the current to flow, okay, without any interruptions. So yeah, this was with delay. Now like what I want to tell you is that like this system like will be stable for certain conditions. Okay, I will prove the stability conditions later, but for this system to be stable, right, we will have 2 conditions basically, and those are anyways true always, that my zeta should be greater than 0 and my omega and natural frequency should be greater than 0. Basically zeta can never be like equal to 0. Why? This is a damping factor. We'll study this in detail, okay, but by the name you understand there is some damping, and damping means there is some resistance, and I can't avoid resistance in electrical components, right? There will always be some resistance. So this will like practically this can't go to 0, and this omega n, right, omega n is frequency. So frequency is positive, right? Frequency is positive in our like real life systems, hence this also can't go to 0. So anyways the second order system will always be most probably stable. Okay, so yeah, this is one thing. There is also another mathematical thing, that if both my damping ratio and my frequency both become negative, then also system will remain stable. Okay, but that is not practically possible in real life. But if even one of them become negative, then my system will be unstable. Okay, you might think like practically you think that if my damping is negative, right, what does that signify? If my damping is positive, what does that signify? There is some resistance in the circuit. If my damping ratio is negative, that means there is some negative resistance in the circuit. What does it mean? Now instead of opposing the flow, it helps in more current. It helps to flow more current, right? Whatever current it was flowing, it helps to flow more current. So it is like a unstable system, right? Because it is increasing the current even further. It is increasing, keeping on increasing, right? It is not trying to reduce it. So it is like an unstable system. It is going unbounded, right? It is not bounded. It is going unbounded and not bounded, right? So yeah, so that's like that is what like negative damping ratio means. It means negative resistance. Okay, and obviously like frequency negative, we have frequency components, okay, on the left hand side for like Fourier transform, all those things from that you can understand. But in real life there is no negative frequency. Okay, so yeah, this was one thing. So why are we concerned for stability? Basically, if the system is stable, then only we can understand the performance, right? So that is we'll talk about the performance of the system in the next few lectures. So if we don't understand like if the system is stable or not, then we won't be able to go to the performance analysis, right? First is stability. Okay, now what we'll do, I will do like few questions. Okay, I told you about the standard and non-standard form of second order differential equation, right? So now I have, okay, this is given for the given transfer function, find damping factor and natural frequency. So damping factor I have told you and natural frequency I have told you. So pause the video right now and solve these, right? Solve these two questions. Okay, pause the video, solve these two, and then pause the video and then solve these two. Okay, so you might notice that these aren't the standard format, right? Standard format was something else. So for the first question, how will you solve? So the first question, right? Basically, I have to find omega n, but is it in standard format? So standard format was d secant was 1, right? So here d secant is in 1. What is the d secant? So d secant T0 equals to 100 by 0 plus 0 plus 400, right? So it is basically equals to 1 by 4. Okay, basically equals to 1 by 4. Now what is my, so d secant is 1 by 4, so I can replace this to my standard format. Okay, anyways, if you want to find the natural frequency and the zeta, right, you look at the let me paste this here, you look at the numerator always. Okay, you look at the numerator. Okay, but I will convert this into standard form first. Okay, so this is not standard form, not standard form. Okay, so what I will do is simply make this 400. Okay, okay, make this 400 times 1 by 4, right? This remains same. Okay, this remains 100, but here this is the d secant and this is the standard format, right? This is standard format. So what is like 400 equals to 400 should be equals to my natural frequency whole square. So omega n equals to 20. Okay, 2018 per second basically. So yeah, now right, I got the omega. So now this is, what is this equals to? The coefficient of s equals to is 2 zeta omega n, right? That was written here basically, this one, right? The coefficient of s is 2 zeta omega n. Okay, so this will be my 2 zeta omega n equals to 10, right? 2 zeta omega n equals to 10. So omega n I know. Okay, zeta I have to find. This is 5 divided by omega n is 20, right? It's 20. So what is my zeta? Zeta is 1 by 4, which is equals to 0.25. So what is the significance of this one? We will understand when we will study about the what do you say, damping factor, right? Damping ratio basically. So this was the first question. Okay, so now let's go to the second question. So second, so is this in the standard format? So what I can see is this is not in the standard format, right? Why? Because the coefficient of s square isn't 1. The coefficient of s square is some like non-unity value, right? So what I will do, I will take common of the coefficient of s square so that this becomes 1, right? So now if I take common, this becomes, this is not standard. That's why finding the omega n from here is risky, right? If you find omega n from here, what you will see? You will see that it is 4, right? But it isn't actually, it isn't, right? So this is, I take 4 common, this is s square plus 2s plus 4. Okay, so what I get this is 4 divided by s square plus 2s plus 4, right? Okay, so again this is the standard format, right? This is what I can see, like these are matching. Okay, so hence anti-secant is 1, obviously. Now I get standard, so coefficient of s square is also 1. So that also I forgot to tell you previously that for standard format the coefficient of s square will be 1. Okay, like during the mechanical system I told you, right? I divided by that term in the second order differential equation. So now what is my omega n square? Omega n square is 4, so my omega n equals to 2. Okay, Now my 2 zeta omega n equals to 2, okay, equating this one coefficient of s, okay. So my zeta equals to 1 by omega n, which is 1 by 2. So my zeta is 1 by 2. Zeta basically is 1 by 2. Now let's solve for second one. So if you would have solved from here, right, just normally you put omega n square equals to 4, 16, you get omega n equals to 4, which is again wrong, right. And you put 2 zeta omega n, that is 2 times 4, 8 equals to 8 itself. So you get zeta equals to 1, which is again wrong, right. So yeah, these things you have to be careful about. You just can't blindly put everything, right. So yeah, now let's go to the third question. Right. So third question, what we can do is, we can, like, this is not standard format. Why? Because I'm getting some different response here and some different response here, okay. So basically I will replace this like this one, s by s square plus 2s plus 4s plus 4 by s square plus 2s plus 4s, okay. So what I am observing is, basically this is the standard format and it is getting multiplied with s, okay, getting multiplied with s. Obviously 4 is not there, but still, if something is getting multiplied with s, then what is happening? Basically there is some differentiation, right. So whatever response I will get from here, I will differentiate this one, okay, and that will be my response, right. So just what is like not standard about this, why is this not standard format? Because both of these terms will give me different responses, okay. One will be one thing, another will be the differentiation of the other, right. So here not standard. Why? Because we will get different responses. Okay, that's why, like, the nature of responses will be different. Nature of responses, or you might say, okay, you might say this one also, we will get different responses, okay. This, but what is the omega n and zeta? Tell me, what is the omega and zeta? Is it 2.5 or is it not, okay, or is it something else? So in this case, right, omega and zeta are 2.5 only, right. So omega n equals to, basically omega n square equals to 4, because this is my characteristic equation, right, this is not changing, okay. So which is equals to omega n equals to 2, and what is my zeta? Like I do 2 zeta omega n, okay. 2 zeta omega n equals to simply 2 only. So zeta, right, zeta equals to 1 by omega n, which is 1 by 2. So what I see here also, zeta omega n was same, okay, omega n and zeta, here also the omega n and zeta are same, okay, but the responses I will get a bit different, okay, because this is their nature of responses will be different, but zeta and omega n will be same, okay. So yeah, I think, yeah, that is it for this lecture, okay. This one was not like a too heavy calculation intensive or concept intensive. This was basic example only, right. So like basic lecture only, because you just had to listen, right. So with start, what is the main thing? I had to put the concept of damping in your head, right. So what does damping mean? Damping means to stop the oscillations, right, to stop the oscillations, like the oscillative behavior that I am getting, we provide damping to stop the oscillations. Now sometimes what may happen, I over damp the system, then I don't get oscillations at all, but I reach to my output very slow, okay. So what is the example of this one? So I will also explain you the example of this one, but here, right, this one, you can take this overdamp system like a door closer, right. So if I tighten the screw too much, then my door will close very slowly, right. So what does that mean? That means that it has been damped very highly, right. So it is not closing, it is not reaching a steady state quickly, right. It is taking too much time to reach its steady state. So that is what overdamp means. So we will, like, I will tell you the examples of all those things in when we will study the damping factor. For now, I just gave you a brief overview of mechanical system in relation with electrical, because electrical you can't see anything, right? You can only calculate current, voltage, all those things, but with mechanical you can see that this dashpot is providing some damping to this mass, because if I give this mass some force, what will happen? This will go here, then due to this spring and due to this dashpot, it will again come back, right? And it will keep on oscillating around this midpoint, right? Keep on oscillating around this midpoint, but this dashpot will help reduce that oscillation. Okay, that's why I like gave you a diagram and all those things to explain you like visually, right? Because in like electrical circuits, obviously we can't see visually what is happening, but when we plot the graphs and the response, there we'll see how visually it is happening. Like visually is basically this one only. Okay, so yeah, that is basically the end of this lecture. Thank you for watching, and in the next lecture we'll study about the damping factor basically.